Hello guys, today we're going to review circular motion. Circular motion. We're going to start with some kinematics involved in circular motion. And then we're going to talk about the dynamics part of it. So first we're going to use variables as displacement, velocity, and acceleration. That is the kinematics part. Kinematics, displacement, velocity, and of course acceleration. And then dynamics, that's part 2. There'll probably be a separate video, but here's the plan. Dynamics. So when you start thinking about things like force and mass, okay, like what is the source of the acceleration? Acceleration is defined as the change in velocity. Velocity is a vector, and it may change in a couple of ways, being a vector, which is a quantity with a dimension and with a direction and magnitude. And the change in velocity leads to acceleration, which is also a vector. Displacement is also a vector as well. And velocity has to do with the change in position, which is displacement. All right? So again, what is the root cause for acceleration? That is force. So once we involve force, therefore mass, which are related to acceleration, we call this dynamics. All right, so you already know what to do in the case of linear motion. All right, we already know these things: displacement, velocity, and acceleration, and force and mass through Newton's law. Newton's laws, especially the third law. Second and the third laws. The first law is about the relation between moving along a straight line in the absence of any forces. The second law relates the acceleration mass to force. And the third law, the action-reaction principle, has to do with those pairs, action and reaction forces. Okay, so let's start with basics. So what will be the displacement variable? A circular motion. Now, circular motion can be 2 types. All right, of course, the particle has to move in a circle, that's for sure. But is it moving with constant speed or changing speed? All right, speed. What happens to speed? The instantaneous speed around the circle of radius r, let's say. Is this speed changing or not changing? Well, that will determine whether the motion is a uniform circular motion or non-uniform. Okay, I mean, both have r, okay? But the speed does not change for uniform. Constant speed. All right. Now, if you assume that the moon goes around the Earth in a perfect circle with constant radius, okay, then the speed of this satellite is constant. So that could be an example. In reality, Earth going around the sun, for instance, is not really a uniform circular motion. It's not even a circle, it's an ellipse. So it's an elliptical motion. It's close to a circle, but not exactly a circle. So if I exaggerate the orbit of Earth around the sun, it's an ellipse. And when the Earth goes around the sun in an ellipse, it slows down and accelerates and speeds up, all right? So that's non-uniform. That's non-uniform. Or let's say you have a washer and dryer, okay? This is your washer, and you turn on the washer, so it starts spinning, right? It won't reach its operating speed in the beginning. It's going to take some seconds, maybe two or 3 seconds to reach that maximum speed, all right? It's going to speed up. That's another example of a non-uniform circular motion. In this case, actually, we're talking about the point on the rim of the drum of the washer, right? If you think about the washer or the drum itself, it's a 3D rigid body. So we're talking about a rotation, all right? An object rotating. That's actually not today's topic. We're only thinking about point particles, all right? When I said moon around the Earth, well, if you compare the distance between the moon and the Earth and moon's radius, well, moon's radius is much smaller, right? So you can think of it as a point particle, all right? So that example is okay. But if you're thinking about objects that are rotating or evolving, like a door, evolving door, that's rotational motion. And the analysis of it requires a little bit more, especially the dynamics part. All right. So today we're going to be doing only point particles going in circles. All right. So the speed. Now, in general, if you remember from our discussions in kinematics, in 2 or 3 dimensions, let's remember those. So you have, let's say, 2-dimensional motion, okay? A flying in the room. Okay, so flying like this is the path of the fly, all right? And here's the fly at t equals 0. This is when you start your stopwatch. At a later time, the fly is here, t, okay? So remember, I mean, this is only the path of the fly. Don't confuse this with your position versus time plot, okay? That's a different story, right? Let me just draw an example of that here. Let's say you take the x-coordinate and you plot it as a function of time, all right? You get something like this, all right? This has to be a function. This is not a function. It's just a path. So you may have loops like this, all right, on the xy plane. And if you want to add, you can add a z. You don't have to worry about that too much right now, but this can be any shape, all right? Just depends on what the fly is doing. So please don't confuse this with that kind of position time plots. Actually, in this case, you will have 3 of those. I mean, how does x change with t? How about y? How about z, all right? So this is a path. What about the position of the fly? How do we define it? Well, we need a position vector, all right? So a position vector starts from the origin. Oops. Starts from the origin and simply points at where the object is at that time, right? A vector. This is the position vector. R stands for radial, if you will. So R, okay, let's call it R0 or R0, because at that time t equals 0. And when the object is over here, over there, we have a new position vector like this. All right, let's just call it R. Vector R. So this R is the position vector. R is the position vector. R depends on where you pick your origin. All right. So Mike's origin is here. Sally has origin over there. So they will not agree on what the position is in terms of the position vector. The position vector is just a collection of three numbers, X, Y, Z. So Mike will have a set of X, Y, Z, and Sally will have another set of X, Y, Z. They won't be the same because their origins are different. But there's only one path and one position, really, or let's say physical location for the object at that point. So that's itself, R itself is not a good variable to work with, all right? So instead of working with the position vector, we need to use that displacement that I was listing earlier, displacement vector, okay? Displacement. So what is displacement vector? We subtract R0 from R. Call it delta R. The Greek letter delta in physics is used for differences. In this case, difference of two vectors. R0 subtracted from R, that is your displacement vector. Now that is the same for all observers, no matter where they pick their origin. All right, so that's R. Okay, be patient. We're going to come to the circular motion. I'm just reviewing our variables, displacement, and you may recall what we did in class with this delta R. Well, you can divide it by delta t. Okay, this vector, delta R, is a vector, displacement vector. We divide it by a scalar, which is delta t, simply t minus t naught, right? That's the time interval we're talking about. So this ratio, this rate of change of position, let's say, we call it the average velocity. Average velocity, which is also a vector, right? And then, if you do this for a very short time interval, very short, so you move just a little bit, all right? We're going to call this ratio, this fraction, the instantaneous velocity vector, all right? It's only the average right now. Now, before we do the instantaneous velocity, let's just try to draw this. Now, do I have a different color here? Let me go up here and see if I have, yes. So let's use red. Okay, I'm gonna go from here to there. This is nothing but delta R. Okay, hopefully you remember how to subtract the vectors, right? Actually, you don't need to know a rule about subtracting vectors. All you need to do is to remember how to add vectors. So in this case, if I add R0 to delta R, if you remember the rule of adding vectors graphically, tail to tip rule, from the tail of the first vector to the tip of the second vector, which is delta R in this case. So R0 plus delta R. All right, let me just write it here. R0 plus delta R gives you R, which is nothing but this, written differently, right? But that's to show you where delta R is. Now this guy here, okay, the average has to be in the same direction, all right? When you have a vector equation, both sides should agree in direction. So the average velocity is also in this same direction. Okay, let me use blue to show. Hang on, let me use blue to show the average. Now, as long as it's parallel, it's fine. So I'm just going to draw it here. This is your V average. Okay. Now, the length of this arrow that I just drew here, V average, is just for a representation here. I mean, it's not really correspond to anything, okay? You can't compare apples to oranges. So the length of this vector here, you know, is some arbitrary thing I just drew. It has nothing to do with the actual distance here. This distance is meaningful because that's this side of the triangle here, which corresponds to the actual displacement. I mean, the object followed the path like this. We're not talking about the line length, if that's a word. Like, we're not talking about, I mean, this could be anything, you know, it could just go all the way and then come back to this point again. All right, we're not interested in that when we say displacement. Displacement is just a straight line. So that's meaningful, but the length of this average vector has to do with time. We're scaling this vector delta R with this constant delta t, or 1 over delta t multiplication, if you think of it like that. That's what your scalar does. It scales things. Okay, so it's just a representation there, but the important point is the blue vector is parallel to the red vector. These two are parallel. All right. Okay, now, while this is happening, okay, let's take a look at what's happening to the x coordinate here. All right, in time. So you're here. This is, actually, you know what? Let me switch back to the color here. Black, all right. So let's say when t is 0, x has a certain value. Let's say this value here. All right, so this is where t is 0, and this is where you are when time is t, okay? So the displacement is from here to there. That's your displacement in x, okay? You will have such displacements in y and z as well. But the point is, we need to divide that displacement by displacement in the x direction by the time interval. So this here is your delta x, or the length of delta x in this picture, while this is delta t, all right? So if you look at the ratio delta x over delta t, you're pretty much talking about the slope of the line that joins, let's use yellow, the slope of the line that joins these 2 points right there, okay? That line has a slope, and the slope can be found by dividing this side of a triangle to that side. So it's delta x over delta t, all right? So if you do this at a shorter time interval, what happens? Okay, let me pick red, all right? Suppose you pick a point here, another point there. Now we have a shorter time frame, okay? But you're here and up there. So we're talking about the slope of this line now, which is different from the slope of the first line, the yellow line, right? But the time interval is shorter. So keep doing that. I mean, consider smaller and smaller time intervals. So you will get different lines like this, but then at one point you won't be able to do this anymore. Like you run out of space, right? So what you will end up with is right there, you will be finding actually the slope of this tangent line here, right there. Okay, so the slope of that tangent to the position time curve at that time, which is this time here, t, well, that is the instantaneous velocity. Okay, I'm just going to write v there. That's the instantaneous velocity, not the average, but the instantaneous. Instantaneous velocity. Now imagine doing this not for x, not only for x, but also for y and z. So let's call this vx. You will have vy and also vz, right? So you will end up with this vector here, v, which is nothing but, okay, vx I hat plus, if you remember the unit vectors, right? Vy j hat, vz k hat. Okay, so this vector that you will find from these vx, vy, and vz is nothing but this at a very short time frame. Technically, we call the limit when delta t goes to 0. Limit delta t goes to 0. For those of you who have taken calculus, we call this a derivative, but if you've never seen calculus, don't worry about it. Okay, delta r over delta t. Okay, that's not really a formula you can use in problems, okay? It's just a representation of what I was doing here 5 minutes ago. All right, it's just this operation here of looking at the motion of an object at a smaller and smaller time interval. Okay, that's called instantaneous velocity. All right, so what about acceleration? Acceleration is the change in the velocity vector, this instantaneous velocity we just defined here. If it changes, this means it's an accelerated motion. All right, so how does it change? Well, to see how it changes, we actually need to know what the vector itself looks like in our original graph here, right there. We have the position and displacement vectors, but how do we draw the instantaneous velocity vector? Not the average, the instantaneous. All right, so let's use, okay, what color? How about green? Let me use green. Now, these vectors will be along the tangent line to the actual path at that point. So this will be v, the instantaneous velocity, v naught at t equals 0. Similarly, right here, the tangent to the path is like this. So the instantaneous velocity will be pointing this way, v. Okay, again, the lengths of these vectors are just arbitrary. I just drew them, okay? They don't correspond to any physical distance. Don't make sure you don't confuse this with delta r. So it changes though, all right? I mean, even if the length doesn't change, when a fly flies in the room, maybe the speed is not changing, but the direction obviously changed. Okay, that's enough to have acceleration. So it counts as an accelerated motion because it changed, right? So let's subtract v naught from v. Okay, this will be called delta v, of course. Remember, delta is difference. So that's delta v, v minus v naught. Why do I need this? Because I'm going to do the same trick I did over here. I'm going to divide it by delta t and call this average acceleration vector. All right. Now, the direction of this vector, where does it point at? Okay, now that's important. Now, of course, I could write this. Do you mind if I switch back to black? Okay. Now, just like I did over here, from delta r, definition of delta r, I wrote r as r naught plus delta r. I'm going to do the same trick here. I'm going to write v as v naught plus delta v. All right, but I need to be careful when I actually draw delta v here. Why is that? Because these two vectors, v and v naught, are not lined up so that they start at the same point. Okay, they just, v naught is here, v is over there. Compare that to r naught and r. They both originate here, right? That's the origin. In this case, how am I going to make this triangle so that I know what delta v is, right? But it's okay. It's not a big deal. Now, this is a flat space. On a flat space, you can move vectors in a parallel fashion, okay? As long as we keep the length of the arrow the same and the direction of the arrow the same, it's still the same vector, no matter where you are. Okay, this is your vector. You can move it anywhere you like in that flat space. Okay, curved space is a different story, but in the flat space, it's still the same vector. So what do I mean? I can take, let's say, v here. Now I know where v is, right? V is along this tangent line here. I can carry that. You know what? Let me actually get rid of this line I just did here. Doesn't really look like a line, okay? Instead, let me use actual line here. Let's see if this will work. Yeah, that's the line, right? Now, what happens if I carry this line over here? Okay, the direction did not change, so I'm going to take v naught and draw it again. Okay, let's go back to green. That was the color I used for drawing v. So v will start here. Something like this, right? That's your v. Same vector, nothing changed. If the length is the same, same vector. But now they start at the same point. And I know how to draw v minus v naught. Just remember what I did for delta r, right? I can do the same for v's now. Okay, let's use, okay, what color? What is this, purple? Something like that. Okay, so v naught plus delta v will give me v. So v naught plus which vector gives me v? V naught plus this guy gives me v. So this is delta v. All right? Okay, so that will be also the direction of the average acceleration. So the average acceleration in this case will also be in the same direction. So same direction, this direction, that is. That is A, average. All right, so this picture is getting cluttered. Sorry about that, but I'm going to draw something like this again here. When I show you how to find the acceleration for a circular motion. All right, actually, let me just draw it since I mentioned it. In the case of a circle, not this arbitrary shape, but just a circle. All right, so now this is r in length. This is also r. That's the thing about circle, all right? So these vectors here are not and r are both equal to r. That's what it makes a circle, right? And the velocity vectors, remember they are tangent. So if the circle is going counterclockwise like this, okay, this is probably, not probably, this is V naught, and this is V, okay, and this is 90 degrees here, and 90 degrees over there, all right? Now, if you want to find delta V in this case, you have to parallel transport. That's what we did here. Move the vector parallel. We need to parallel transport V to where V naught is, or vice versa. You can move V naught to V as well, doesn't matter. So if you move, okay, almost like this. All right, that is still V. And then you get delta V. Get delta V like that. All right. Now, if this circular motion is uniform, if it is uniform, then V naught and V, although are different in direction, they are the same in magnitude. So if V naught and V are equal, let's just call it V for short, okay, then this is uniform. Uniform circular motion. Okay, we're going to come back to this circle again, but let's do one more thing, and that is considering the limit again. When delta t goes to 0. So you take this limit now, which you know now, okay? That's taking the limit of delta t goes to 0, but not delta r over delta t, but delta v divided by delta t. And this will be defined as the instantaneous acceleration vector, all right? So this will be the instantaneous acceleration vector. What about the direction of the instantaneous acceleration vector? Okay, so let me try to draw an arbitrary path here of an object moving on this plane. Here's my origin, and this is the radius, not radius, position vector, r, all right? And now I know two more vectors. These are the instantaneous velocity, which has to be along the tangent line, tangent to the curve right at this point. So tangent line, therefore, here's the vector, which is instantaneous velocity. And now we also have the instantaneous acceleration. Now, what direction though, right? What direction? Now, I can give you a general idea of what direction it can be based on, let's say, this picture over here. Remember what delta V is doing here? Delta V is pointing this way, right? And I'm dividing delta V by delta T and then taking delta T close to 0. Well, that limit will not really have an effect on the direction. Same thing here, over there, delta V divided by delta T, which is the average acceleration direction this way, right? So if the object is curving to the right, all right, that's where the acceleration vector is pointing at, all right? So in this picture, I cannot have a delta V. It's impossible to have a delta V in this direction, okay? So A cannot be this way. It's impossible. Okay, so it's got to be downward because the curvature here dictates that the acceleration vector has to point similarly. Okay, let's use blue. But how? I mean, is it going to be like this, like 90 degrees with velocity, or like that, or maybe like this? Okay, these are all possible, right? These are all possible. And which one is the correct one, if you ask that? Well, that depends on how V is changing, all right? How V is changing. If this velocity, its magnitude, I mean, if it's increasing, all right? If it is increasing, then acceleration will be this one. If it is decreasing, acceleration will be over here, this guy, for decreasing magnitude, decreasing speed, all right? The magnitude of V is instantaneous speed. If it's not changing, as it is in the case for a uniform circular motion, then this one, which is perpendicular to the velocity vector, that will be the acceleration vector, okay? So the direction changes like that. An alternative way to think of it is by decomposing A into its components. Well, the components are not the XY components, which you're familiar with, but the tangential and radial components. So here we have the tangent line and the radial, or normal, maybe that's a better word, normal. Normal in mathematics means perpendicular, and this is a tangential line. So if you decompose this vector A into its tangential and normal components, okay, let me just show it for one of them. Let's say this one here. How do you do that? You box it, right? You draw a box around it like this, and then you recognize the sides, this one here and this one. These two are the components of A along the tangent line, okay, tangential component, and this is the radial component, radial or normal, all right? So you can write A as a vector sum, a tangential plus a radial. All right, so that's what I mean by components. So if a tangential is parallel to the instantaneous velocity, then you're speeding up. If a tangent is anti-parallel, if they're pointing in opposite directions, then you're slowing down, which means this, all right? If there is no a tangent, there's only AR, okay? Then you're neither speeding up nor slowing down. You're moving along the path with constant speed. That's when a tan is 0. AR is never 0, okay? The path dictates AR. I'm going to show you how to find AR in terms of the radius and speed for a circle. So you'll have a formula for that, okay? And that term is there because you have a curved path. It can never be 0. The only time it is 0 is when you're moving along a straight line. But a tangential, this guy here, can be parallel to V, anti-parallel to V, or even 0, okay? There are possibilities for that. Okay, so let me stop here. In the next video, I'm going to show you how to find AR, the formula for AR, for the special case of the uniform circular motion. All right, let me stop the